So, uh, after the chapter on simple harmonic motion, the harmonic oscillators, etc., we now come to the ultimate chapter in for class 11th students exclusively, as has been designed in several boards in India. Well, waves, they have been, everybody has known since people started their speech and they started using their ears, that there are traveling waves. The traveling waves are a means of propagation, a mode of propagation of energy in space from a point P to another point Q. That could be connected in between. Here there could be material medium and there could not be material medium. We will talk about that. So, one of the questions which we raise is, what travels? Matter? The answer is no. Matter does not travel. So what travels? What travels is a disturbance, which is the key word in the propagation of waves, or what we call a perturbation. Okay, 4-syllable word, perturbation. Disturbance, a 3-syllable word. Anyway, now we know that, and we have just finished with that chapter, that material medium, which may be solid, a liquid, a gaseous medium, but not rarefied gases. Material medium is a collection of elastically connected oscillators which are close to each other. Okay, if one is disturbed, then the neighbor is also disturbed. Okay, if one is oscillating, then the neighbors also oscillate. One of the examples which is given is throwing a pebble in still water. Okay, so what happens? Circular crests and troughs are found. They appear to travel away from the point of disturbance towards the outer edges of that water body, and if we put a cork or some cork pieces, then what we find is that these cork pieces, they oscillate like this on the troughs, which become crests, then troughs, then crests, then troughs, like that, and the oscillation keeps on going. Okay, water mass does not flow outwards with the apparently moving circuits. Okay, and what is created is a moving disturbance is created. Speech, for example, like I am talking just now, and you are listening to it. I'll just tell you about that. In this room, I have air, and my speech travels to my friend over here as a disturbance through air from my mouth to his ears. Ears have got the diaphragms, and I can make vibrations through my tongue and the other things that I use for speaking. But thereafter, it is loaded on the internet and reaches you, and then you retrieve it in the original form. Okay, when you are sitting, you are looking at, and there is diaphragm which is again vibrating, and you are able to listen to it. So that is the way the data are the information. So waves transport energy through disturbance, which contains information from point P to point Q. Okay. In between here, there may be many other things, which I have just shown over here. There has to be a production of the disturbance, and there has to be a detection of them. And when production detection process is there, then we call it communication. In communication, there has to be a kind of propagation of this energy which is transported from one point to another point. In the meantime, like I told you, it may be converted to electromagnetic mode, electrical and magnetic oscillations, which can be transmitted again through cables or wireless, and the electromagnetic waves so formed, they travel across vacuum. From the stars, far off stars, the light is traveling to us, okay, and the speed of light is determined as 299,792,458 meter per second, which is roughly equal to 3 into 10 to the power of 8 meter per second, okay, as it is. Now, let me tell you that waves and the associated phenomena in arts and culture, and particularly what is known as fine arts, has been there from the time immemorial, but they were scientifically studied by three contemporaries. Contemporaries means people who lived at the same time. Of course, they lived in different nations, different places, and they all lived in Europe, and they were investigating what are the various informations, etc. So there comes Huygens, who gave the wave propagation of light. Newton gave the corpuscular propagation of light. And so between them, they solved many a thing which is associated with that thing. So that was in the 17th century. And a lot of progress took place in 17th century. Okay, so I talk about. So we have three broad categories of waves. One is the material waves, which we also call mechanical waves, which actually we are going to study now. Then E by M waves, which we will study when we study the optics and other associated electromagnetic waves. For material waves, we must have a material medium for communication, but here there is no material medium which is required, as I told you just now. Then there is a third category which is called matter waves. Well, in matter waves, we cannot explain those matter waves with the help of the classical mechanics that we have been following, but rather we have to go for quantum mechanics. And there, the particles that participate and travel, they are electrons, protons, neutrons, and atoms, etc. And of course, these matter waves are useful in electron microscope and many other things which are being used in diagnostics these days. Well, as it is interesting that the understanding of physics of waves followed the physics of oscillation of masses tied to springs, which I have already discussed in past lectures, and physics of the simple pendulum, which we have discussed in the last lecture. Okay. So we find that waves in elastic media, gases, liquids, and solids. Solids are the most ordered system, liquids are less, and gases are much less. So very rarefied gases, of course, the gas particles or the molecules are very far away from each other, so that if anything happens to this molecule will not be disturbed. But when they are close in the case of liquids, then whatever oscillations are there are in the case of solids, which are dense materials. There we have a intimate connection of harmonic oscillators. Okay. Now let us see. Just like that, we have a set of 3 springs, massless, this, that, etc., etc. Spring number 1, 2, and 3. Now, what is done? The end of A is suddenly pulled or pushed. So what it happens? Disturbance is generated, and this disturbance propagates to the other end. This can happen if we compress it or if we elongate it. Okay. So first of all, whatever disturbance is here, then the connection is there, the intimate connection is there, then this is the friend, and we'll say, oh, you are being disturbed like that? Okay, he will also get disturbed the same way, and the third one, and the fourth one, and the fifth one, and that way the disturbance will travel. Of course, what can happen later on is that the disturbance may get reflected back, traveling from 3 to 2 to 1. First of all, it went from 1 to 2 to 3. Okay, so they are disturbed one after other when they are compressed or they are stretched. Of course, in any kind of an oscillator, when there is a disturbance, then the disturbance must come back to the original position. And in doing so, there has to be a restoring force which must be proportional to the disturbance. Okay. And there can be compression, for example, in case of air, compression and rarefaction. In compression, the density of air increases. In rarefaction, the density of the gas is reduced. So this to and fro process, compression to rarefaction to compression to rarefaction, as required, as desired, as in the information in the disturbance, there is a propagation of the disturbance or propagation of the information contained in disturbance. Solids, we know that in solids there are arrays and arrays of atoms, and because they are very close to each other, therefore they can be visualized as connected by imaginary springs. So when one atom is disturbed, the other atom is disturbed, the third is disturbed, the fourth is disturbed, like what happens in the case of cycle stand, when cycles are standing very close to each other and you just push one cycle, must have done every one of you, and then all the bicycles they go on falling. One example is given, that of a train of compartments which are connected to each other with means of strong springs. So when the engine pushes one of them, then that is communicated to all of them and they start moving like that. Okay, so these are the material waves which I am talking about. Next I talk about the two other categories that are transverse and longitudinal waves because of transverse and longitudinal disturbances. So very briefly, I will tell you about the transverse and longitudinal categories of waves, which you have learned in your high school classes. Okay, I'm just taking a schematic of the wave propagation in this direction in both the cases, and here a particle is, or whatever is disturbed, perpendicular or transverse to the wave velocity. Okay, what does that mean? Transverse means that if the wave is propagating towards you or it is propagating away from you, you can see that each line over here, each set of lines, they make an angle of 90 degrees. Okay, so this is what I mean by transverse waves. They can be, the wave velocity is v, but the velocity of the oscillating particle keeps on changing, like in the case of simple harmonic oscillator. Okay, this is the case of longitudinal waves. The longitudinal waves go along the direction of propagation. Okay, and this is the case of, for example, air or in many gases. This is the kind of waves which exist in those systems. When I am speaking, it is goes through rarefactions and compressions in the air. So this is another thing. Well, the solids have bulk modulus and shear modulus associated with them. So they are both categories. Category this, also category transverse. Okay, the possibilities. So the gases and the liquids normally have the longitudinal waves. Next we come and we discuss we obtain an equation where the disturbance is a function of its x component as well as t component. This is space and this is time. Okay, this is makan and this is zaman. Okay, so in a space-time continuum, I have the disturbance, and this disturbance is one of the representative equations is a sine of omega t minus k, kx minus omega t plus phi. When we have t is equal to 0, r, the value of t is fixed, so what we get is a sine of kx plus some constant, which is a simple harmonic oscillation. With respect to the space coordinates. Okay, and if I have the value of x fixed, so we can find out that this plus this will become a constant, so it is equal to a sine of minus omega t plus some constant, and therefore it is a kind of a simple harmonic motion with the frequency omega, angular frequency omega, their frequency nu and time period capital T. This K we'll discuss in the next lecture. Okay, this is called this is 2 pi upon lambda. Okay, and this is called wave number. So these things I expect you to come back after looking at the description of what are the transverse and what are the longitudinal waves, and then we build up an equation like that and explain that and how the various plots in time and in the space coordinates that can be made and that can be understood for the progressive wave. For progressive wave there is another name, and that is called a traveling wave. Okay, so there are stationary waves, but they are not waves. Okay, that's a misnomer. We'll talk about those things in the next outing. So today what we have done is we have introduced waves as the means of propagation of energy from one point in space to another point in space. I've told you broadly there are three categories. One, where the mechanical waves that we are talking about and we'll concentrate on, they are due to the elastic properties associated with the medium, where they are connected, the atoms etc. are connected by an imaginary massless spring, which is not there of course, but for understanding we do that. And in many things like guitars, sitar, this, that, transverse waves are generated, but then the air is disturbed, converts into longitudinal waves and come to our ears and diaphragms of the detecting instruments, whatever is there. Even in the case of what you call drums, they again travel to the gases that way. So friends, I will enjoy if you come prepared about the wave phenomena that we have just discussed. Even if you go to your high school book, that will suffice, and when we meet again, we'll discuss the intricacies of the wave equation, energies etc. which are transmitted or which are propagated. Thank you very much. See you again.